In this video, we are going to discuss about AES or Advanced Encryption Standard, which is most widely used block cipher nowadays. So almost everywhere in banking systems, in your debit card, for securing any account, most of the time we are using Advanced Encryption Standard. So earlier we understand about DES, Data Encryption Standard. Now we will go into the detail of Advanced Encryption Standard. Classes introduction, we will first have an introduction about AES, what is AES, then we will understand the structure of AES, like it follows four basic operations: byte substitution layer, diffusion layer, key addition layer, key schedule, then how decryption, and what are the issues of advanced encryption under advanced encryption standard. So first let's understand just a bit introduction about AES. So AES is most widely used symmetric cipher today. The algorithm AES was chosen by US National Institute of Standard and Technology (NIST) in a multi-year selection process. The requirements for all AES candidate submission were block cipher, like these were the requirement which is generated by NIST, that there should be a block cipher with 128-bit block size, 3 supported key length 128, 192 and 256. Then security relative to other submitted algorithm, efficiency is in software and hardware. So at that time, the need for a new block cipher announced by NIST in January 1997. 15 candidate algorithms are accepted in August 1998, and there were five finalist announcement in August 1999, namely MAS, it's from IBM Corporation, RC6, RSA Laboratories, then Rindle, J. Damon and V. Risman, Serpent, Elibeham et al. And Two Fish, B. Schinner et al. So in October 2000, Rindle was chosen as AES. So it is primarily known as Rindle, with the name of Risman and Damon it is given Rindle, and now it is popularly known as AES or Advanced Encryption Standard. AES was formally approved by US Federal Standard in November 2001. So what is AES? Let's discuss it in detail, that what is AES. So it is a block cipher. This AES is a block cipher. It means it has a block of input and it gives us a block of output. So namely there is 128 bits of input and which gives us 128 bits of output. Then it has some key also. So key size is also 128 bit. Key size is also 128 bits, and it is a block cipher. AES is a block cipher. So there are three versions of AES basically. So bit size or number of bits n is 128 bits, and key size k, or let me write key size, this is also 128 bits. Then there can be three versions. First one is when R or round 10. Then second one is, in second version rounds are 12, and in third version rounds are 256. Sorry, rounds are 14. So for round size 10, key size is 128 bit. For round size 12, key size is 192 bits, and for round size 14, key size is 256 bits. For all of them, the size of input is 128 bits. So these are the three versions. This first one is known as AES 128, namely AES 128. The second one is known as AES 192 because of the key size is 192 bits, and the obviously third one is known as AES 256. There are four basic operations for AES. So there are four basic operations. We will discuss all the operations in detail also. So first one is add round key. Second one is mix column. Third one is, sorry, second one is sub byte. Second one is sub byte operation. So second one is sub byte operation because it works byte wise. So third or it has 8 bytes S box, then shift row, and the last one is mix column. So we will discuss all these operations in detail also. So first what we do initially, let's say we put a 128-bit input, and the first one is we add round key. So we generate round keys also, we add round key, and let's say this is K1. After this, shift byte, sub byte, after that shift row, then mix column, and after that we add round key. So this is in the first round we add an addition round key in the beginning, and this round key is known as K2. So this is, this is first round, and similarly we run R minus 1 rounds. So these are all R minus 1 times we do the same thing, add round key, sub byte, shift row, mix column, and after that for the rth round we do not add round key. Here we say sub byte, then shift row, then add round key at the end. And then we generate 128 bits of output or ciphertext, that is Y. This is K of R plus 1. So mix column is not present in the last round, and this add round key, this is the only for the first round, otherwise we start from here for the R minus 1 round. So this is a typical AES structure. AES 128 bit and 10 round block cipher. Here key size is 128 bit, plain text is of 128 bit, which is going to generate a 128 bit ciphertext, and it will be like X, add round key, then sub byte, then shift row, then mix column, then again add round key. So after that again we will go for sub byte. So this is typically, and it will run for the 10 rounds of AES. So this is how a typical AES 128, this is the most used version, AES 128 bit version. So this sub byte or substitute byte operation uses an X box. This operation uses an S box to perform a byte by byte substitution of the block. Then this shift row is a simple permutation. This is a simple permutation. We will discuss all these operations also in detail. This is a simple permutation. Then this mix column is a substitution. That makes use of arithmetic over GF 2 to the power 8. So it is a substitution which use an arithmetic over Galois field 2 to the power 8. And a round key is a simple bitwise. It's a simple bitwise XOR of the current block with a portion of the expanded key. So we will understand what is the expanded key, what is this sub byte S box, what is this shift row. We will understand all these things. So let's first understand the sub byte operation. So in DES it is like byte wise. So S box and by 1 byte is equal to 8 bits. So let's say this is the S box and it has 1 byte. So 4 bits and 4 bits, combination of 8 bits is 1 byte. So this is the S box entry, and first 4 bits represent column and these 4 bits represent row. And similarly we generate the output in 8 bits, which is going to be the output for S box. So let's check S box for DES, like for example S box for AES. So like for example, let's say the number is 53. So when we say number is 53, so this is hexadecimal entry. So this is 5th column and like 3rd row, let's say 5th column and 3rd row, it gives us a value 96. So 9 and 6 will be converted into bits and it gives us the output. Similarly, we talk about 7th row and 6th column, the answer will be, output will be 38. So this is something like how we work with S box or substitution bytes. So this is how we work with S box in AES. Now let's talk about the shift row operation. This shift row operation of AES, here is some like what we do, we divide in AES is a bitwise, so we write it in state wise operation or bitwise operation. So what we do, like for example, let's say our plain text is of 128 bits. So what we do, 16 bytes, we divide it into 16 bytes. Okay, so let me write it like this. Let's say x1, x2, and all these x1, x2 are bytes up to x16. So 8 bits here, 8 bits here, and 16 into 8, it is 128 bit. Overall it is 128 bit. And what we do, we can like represent it in form of a matrix. Like for example, this matrix is S00, S10, S20, S30, then S01, S11, S21 and S31. Similarly S02, S12, S22, S32. Similarly S03, S13, S23 and S33. So this is state wise operation. This is state wise operation and it has 4 into 4 bytes. So state wise operation, and every state represent a byte. Every state is going to represent a byte. It is a 4 into 4 matrix. So suppose our plain text is like, we divide plain text into 16 bytes. So we are going to write our plain text like x1, x2, x3, x4. Then from here x5, x6, x7, x8. Then x9, x10, x11, x12, then x13, x14, x15 and x16. So this is how we represent our plain text into states. So when we say the first operation, where we talk about this add round key, this is just simple bitwise XORing. Whatever key we have, we bitwise XOR that key with our input with these input bits, and we pass that key. So first add round is just simple. Whatever key we have, we simply bitwise XOR that key and then pass. And this is our sub byte operation, how S box works. Now the next operation is shift row. So what we do in shift row, first row remain unchanged. First row of this state wise matrix remains unchanged. So first row remains unchanged. Whatever is the first row, that is going to remain unchanged. Second row, one time circular left shift. One time circular left shift. Third row, two times circular left shift. And the fourth row or last row, three times circular left shift. So how it is going to be changed? For example, this is our matrix. So let me write state-wise matrix. So for example, this is our state-wise matrix. S00, S01, S02, S03. Then S10, S11, S12, S13. Then S20, S21, S22, S23. Then S30, S31, S32 and S33. After the sub-byte, after the shift row, it is going to be like this. This is our matrix. And what we say, that first row remains unchanged. So I am going to copy first row as it is, S00, S01, S02, S03. Then second row, one time left circular shift. So it is going to be S11, S12, S13 and this S10 will be added in the end. Then third row two times, so it means we will shift these two at the end. So it will be S22, S23, S20 and S21. Now the fourth row is three times. So it means we will shift all these three at the end. So it is going to be S33, S30, S31 and S32. This is how shift row work. So if we talk about algebraic formulation of AES S box, so when we talk about when we talk about DES, the S boxes are just simple permutations. Okay, so those S box entries are arbitrary permutations. We do not know from where those entries are have come, and those were the fixed X boxes. So S boxes in AES box in AES is also fixed, but it is not a random AES box. We can calculate. We can fix. We can check how this S box is. How the calculation of this S box is done in AES. So the AES S box, how we generate the AES X box. So let's write it. So let's say we have a finite field F to 8. All the operations are done the finite field F to 8. So it is also known as Z to X, set of all polynomials whose coefficient. Z to X means set of all polynomials whose coefficients are either 0 or 1. Either 0 or 1. So this is there is an irreducible polynomial over this F to 8 is x to the power 8 plus x4 plus x3 plus x plus 1. So this is the irreducible polynomial, and this is used for AES S box. So this polynomial is used for AES S box. So like for example, what we write, let's say this is S box, and all the entries of this S box are 8 bits are A0, A1, A2, A3, A4, A5, A6 and A7. and it generates 8-bit output. Then how this, let's say this is B0, B1, B2, B3, B4, B5, B6, B7. So how this A4, B4, B1, B0, B1, B2, B3, B4, B5, B6 and B7 are generated. Basically this is a sub-byte operation and converting this into a field. So sub-byte means we are converting this into a field. So first one is, we write a field, we write a polynomial is z, which is based on these input a0 plus a1x plus a2x square up to a7x to the power 7, and this z should belongs to f2 to the power 8. Second thing is this z cannot be equal to 0, then only z inverse exists. If this is not equal to 0, then we can say that z inverse exist. Third is this z inverse should be alpha 0, alpha 1x plus up to alpha 7 x7. Next is this a7, a6, a1, a0, we calculate for all these alpha 7 alpha 0 to alpha 7 for all this a1, a2. Now there are some constants given by design, which are C7, C6, C0, C1, C2, C3, C7. This is, the constants are 1, 1, 0, 0, 0, 1, 1, 0. So these are the constants given by design. And for all I is equal to 0, for all I is equal to 0 to 7, how we generate BIs? BI is equal to AI plus A of I plus 4 plus A of I plus 5 plus A of I plus 6 plus A of I plus 7 plus CI mod 2, because these AIs are only two constants, and then we return B0 to B0, B1, B2 up to B7. This is how we generate these B0, B1, B2, B7. So let's take an example. Let's say the number is 53. Let's say the our input or x is 53. So when we say the x is 53, if we are going to represent this 53 into hexadecimal form, it will be 0101 0011. So this is like, we say that this is our input to S box. This is the input to S box. So you can say that this is A0, A1, A2, A3, A4, A5, A6, A7. Okay. So what we do? This is 0. So the polynomial which we represent, the polynomial which is represented by this is x to the power 6 plus x to the power 4 plus x plus 1. If we calculate multiplicative inverse, like we need to do here, what we are doing here, we are calculating multiplicative inverse. So if we calculate multiplicative inverse for this polynomial using extended Euclidean algorithm, it comes out to be x to the power 7 plus x to the power 6 plus x cube plus x. So x to the power 7 plus x to the power 6 plus x cube plus x. Now now what we are going to do? We are going to convert these A7 alpha 0 alpha 7 to A0 A1 A7. So now A0 A1, now A0 A1 A2 A3 A4 A5 A6 and A7. So if we check from this is alpha. So this A0 is going to be 0 because there is no A0 for 1. Then for x it is, so it is going to be 1. Then x square, it is absent. X cube, it is 1. x4, x5 0, x6 is 1, x7 is 1. So there is no coefficient. Where there is no coefficient we put 0. So now this is our a0, a1, a2, a3 when we generate the multiplicative inverse. Now using this formula we can generate b0, b1, b2. So let me write for b0. So b0 will be like here a0, then ai plus 4 means a4, ai plus 5 is a5, ai plus 6 is a6, ai plus 7 is a7 and c0, and it is mod 2. So a0 is 0, a4 is a0, a1, a2, a3, a4. a4 is also 0, a5 is 0, a6 is 1, a7 is 1, and the constant c0 which is given here, c0 is 1. So we put 1 also here, and when we do mod 2 operation it is going to comes out to be 1. So in this manner we can calculate b1 also. So b1 will be a1 plus a5. This is how we generate x box for AES. a7 plus a0 plus c1 mod 2, and when you calculate it comes out to be 0. Similarly we can calculate all other b1, b2, b3, b4 up to b7, and when we put it, it is like this. It comes out to be this, and it is 1110. So this is b0, b1, b2, b3, b4, b5, b6 and b7. So this is the output of S box when input is 53. When input is 53, the output of X box is this one. Okay, for input 53, the X box gives us this, and if you represent it in hexadecimal, it is ED. So now we will confirm from the S box table that whether we calculate it correctly or not. So S box says so this is S box. So fifth row and third column it comes out to be ED. Comes out to be ED. So this is how we calculate S box. So this is about S box of AES. Then in the next video we are going to discuss about all other operations of AES. Thank you.